Okay, here we are going to review vertical circles, so objects moving in a nice vertical circle. Now, what makes these a little bit different than horizontal circles is we often have more than one force that's combining to give us our net centripetal force, and we're also dealing with the force of gravity acting on the object. So the first type of vertical circle we're going to look like it at is just a ball being swung in a nice vertical circle. So think about like swinging your keys on your finger. We're going to make a couple of assumptions. We're going to make an assumption that the speed is constant throughout the entire circle. And of course, also the radius is going to be constant. So at this top point, we are going to have both a force of gravity and a tension force pointing inward. Now, with vertical circles, it's the net force in the y direction, usually, that gets replaced with the net centripetal force. Okay? Specifically, that is true if we're looking at the top or the bottom. Okay? So here, both Fg and Ft point inward to create the centripetal force. And since they're both pointing inward, we always want to say that into the circle is the positive direction, and these two are going to add together. So they kind of share the responsibility for getting the object to move in a circle. Okay? Now, if the object is just barely making it around, the tension force is going to be approximately 0. So the force of gravity then becomes completely responsible for our centripetal force. Okay? And we can just barely make it around at the top. Then at the bottom, we're going to have a tension force pointing inward. And remember, into the circle is always positive, and an Fg pointing outward. So here, my net force in the y direction is MAC. So I have tension minus gravity here, because they're in opposite directions. So here, tension force has to not only move this thing in a circle, but also counteract the force of gravity. Whereas before, gravity and tension were sharing responsibility for moving in a circle. So here, my tension force would look like mv squared over r minus mg. Okay, whereas here, they are plus, right? And I could replace that AC with v squared over r. Now, the last point that we might look at with an object moving in a vertical circle is when we're kind of perfectly horizontal. The string is perfectly horizontal. So if that's the case, we'll have a tension force pointing inward and a force of gravity pointing downward. And here, the tension force would be completely responsible for moving us in a circle. So the tension force would equal mv squared over r. So that's what's also a little bit different about vertical circles is depending upon where we are, that changes what forces are creating the centripetal force. Now, because we're moving at a constant speed, this mv squared over r part is always the same. So the centripetal force is always the same, but if we look at our equations, the tension force is going to be changing as we go around a circle. And if you've ever swung your keys in a circle, you can you know this. You feel different pulls depending upon where you are. So based on our equations, it looks like here we are going to have the greatest tension because we have that mv squared plus mg. Here we are going to have the middle tension, middleest tension, so we're just mv squared over r. And then in this first one, we are going to have the least tension because we have mv squared minus mg. Right? This is the least because Fg and Ft combine to create centripetal, whereas this is the greatest because Ft has to create the centripetal and fight Mg. So that's kind of tension forces in vertical circles. The next thing we're going to look at is normal forces in vertical circles. And the first thing we're going to look at is a roller coaster kind of like loop-the-loop. Okay? So we might have a car at 3 different locations, A, B, C, as we go around a loop-the-loop on a roller coaster. Now we're going to pretend that this is a perfect roller coaster, and we are again moving at a constant speed as we go around. So at A, my forces are going to look like normal force and force of gravity. So those two forces are going to combine to give us the centripetal force. At B, just the normal force is going to create the centripetal force because just the normal force is pointing in towards the center of the circle or in the direction of the circle. And then at C, I have a normal force pointing upwards, an FG pointing downwards. And at C, my normal force is going to be responsible for moving me in a circle and fighting FG. So if you've ever wondered why you feel extra heavy at the bottom of the loop-de-loop, that's why, because our normal force is the greatest at the bottom of that loop-de-loop compared to, say, the top, where we might even feel weightless. Now, again, at B, or at point A, we might have this question where we just barely make it around, okay? And if we're just barely making it around, that means our normal force is approximately 0. So if we're just barely making it around, then at that top location, our force of gravity becomes our centripetal force. That's what's keeping us moving in a circle at just this point. So that's kind of like that perfectly timed roller coaster where you feel like you're falling out of your seat. All right, we got 2 more examples. Again, dealing with normal force. This one is going to be going over the top of a hill. Okay, so here we have our force of gravity pointing downward and our normal force pointing upwards. Okay. So our net force is the centripetal force. Okay, and into the center of the circle here, well, this is my circle. So the force that's pointing into the center of the circle is Fg. We said into the center of the circle is positive. So this is Fg minus Fn is MAC. And that is how we would solve that problem, right? Fg minus Fn is mv squared over r. Now, if you've ever gone over a hill relatively quick, you know that there's probably a speed we shouldn't exceed to go over that hill, right? Because we still need to have a normal force. Okay? So again, we can get like a just barely making it over, but in this case, we're really going too fast. And if that's the case, then our normal force is approximately 0. So our force of gravity is completely responsible for moving us in a circle. So you know that if you've ever gone over a hill pretty quickly, you might sort of feel like you're flying out of the seat. That's when this is happening. This just barely, right? You're going basically as fast as you can go over that hill. And then the last type of circle is when we're at the bottom of a hill. Okay, we got a normal force and a force of gravity. And here, the normal force is the thing pointing into the center of the circle. So my normal force is going to be that positive centripetal force. Well, part of the positive centripetal force. But we're still fighting that force of gravity, kind of like at the bottom of the roller coaster. Okay. So my normal force is going to be larger than my force of gravity here. We might feel pushed into our seat because the normal force has to create the centripetal force, but then also fight the force of gravity. So those are our vertical circles that we're most commonly going to see. Lots of normal forces and forces of gravities, and then also some tension forces back in the beginning.